For day number 2, we're going to be looking at Taylor polynomials. Now, we've already been doing Taylor polynomials, but we've just been doing a special type called Maclaurin polynomials. The only difference here is that Taylor polynomials can be centered anywhere that we want. We call the centering point x equals c. For the Maclaurin polynomials from yesterday, the c had to be a 0. That's the only difference. All right, I made a problem up that's a cube root of x is my equation. I would like you to find its third degree Taylor polynomial centered at c equals 8. So again, we're not centered at 0 anymore like the Maclaurins. All right, well, f of x would be the cube root of x. That's going to be x to the 1/3 power. I'm going to rewrite that. And since I want a third degree Taylor polynomial, I need to take 3 derivatives. First derivative will be 1/3 x to the negative 2/3. The second derivative should be negative 2/9 x to the negative 5/3. And using the power rule one more time, the third derivative should be, let's see, negative times negative, positive 10/27 x to the negative 8/3. All right, we want to have this centered at c equals 8, so I'm going to change colors to green. I'll simply change all the x's to 8s. Did you see what I did there? That's pretty slick. All right, 8 to the 1/3 is the cube root of 8. That's 2. And I like to put my little squares around the coefficients. Oh boy, okay. Got to think about this. 1/3. 1/3. I won't write the 1. Yeah, I will. 8 to the negative 2/3 is going to be 8 cube root in the denominator squared. Ah, joy. Let's see what that is. 1 over, okay, the cube root of 8 is 2. 2 squared is 4 times this 3. That's going to be 1/12. Okay. Let's make a lot of room here. Negative 2/9, and it's going to be 8 to the negative 5/3. I already know that the cube root of 8 is going to be 2, so that's going to be a common theme. So cube root of 8, which is a 2, it's to the 5th, and it's negative, so I put it in the denominator. So 2 to the 5th is 32. Oh boy, all right. I can cancel that into the 2. 9 times 16 is 144, so that's negative 1/144. And finally, the third derivative, see if I can fit this in here, it's going to be 10 over 27. Let's see, the cube root of 8 is going to be a 2. It's in the denominator. 2 to the 8 is 256. Yeah, that's right. I can, again, cut that in half. Half of 256 is 128. I'll be right back. I'm going to go grab my calculator. And this makes me so happy. 27 times 128 is 3456. It's kind of cute. All right, I need some room, so what I'm going to do is just simply move the coefficients over and get some blank space. All right, I'm ready to write my answer. The third degree Taylor polynomial is going to be 2. It's not x this time, it's x minus 8. Remember, we're centered at 8. Before, it had just been x to the 0 because you don't have to write the minus 0 in the parentheses, but now we have to be a little bit more careful. Okay, so that has been used. Plus 1/12 x minus 8 to the first over 1 factorial. I like to write this all the way out even though I'm writing extra things, just so you can see my mode of operation, you can see the patterns being formed. Okay, plus, okay, we're on to the second powers. And then finally, we've got the 3 factorial down here, third power. Again, this is second power over here. Just throw the coefficients on. -1, 1/44th, and 5. And I realize I'm making a huge mess. I'm going to fix it. 3, 4, 5, 6. All right, that's my almost simplified answer. My full answer is going to be in this nice box right here. Hopefully it fits. Okay, 0 factorial is just defined to be 1. X minus a to the 0 is 1. That's just a 2. Good, I need some room. This is simply going to be 1/12 x minus 8. This can be simplified to -1/288 x minus 8 quantity squared. And finally, the last one is going to be 5/20,736. 20736. And as crazy as that might seem, it's correct. Look at that. Oh my gosh. All right, let's find the 4th degree Taylor polynomial for natural log of x. All right. Well, thankfully, the derivative of a natural log of x is 1/x, which you can also think of that as being x to the negative first. And if that's x to the negative first, then the second derivative would be negative x to the negative second. And this is great. We can just stick with the power rule the whole time. Positive 2 x to the negative third, and -6 down by a power x to the negative 4th. So thankfully those weren't too bad. All right, now it's not centered at 0, it's centered at 1. All right, let's put the 1's in. Natural log of 1 would be 0. You put a 1 in here, you get 1. This will be -1/x squared. -1/1 squared, of course, is -1. You put a 1 into this, you're going to get 2/1 cubed. That's going to be 2. And finally, this is -6/1 to the 4th. That's -6. All right, 4th degree polynomial. I've got 0. It's not just x. Remember, it's x minus 1. We're centered at 1. X minus 1 to the 0 over 0 factorial. That's just a big 0, but I thought I'd write it. Okay, plus 1. X minus 1 to the first over 1 factorial. Plus -1. X minus 1 to the second over 2 factorial. Moving faster than I realized. Here's 3 factorial, 4 factorial. All right, let's see. 2 and -6 are the coefficients. These are all x minus 1s because that's where we're centered at. And the powers match the factorials to keep my life easy. All right, the final answer will be down here in this blue rectangle. All right, as I mentioned, this is 0. This is just simply x minus 1. Minus 1/2 x minus 1 squared. Plus 3 factorial is 6. That's going to be 1/3 x minus 1 cubed. And of course, 4 factorial is 24. 6 cancels into 24. That's going to be -1/4. -1/4 x minus 1 to the fourth. Do you notice that that is from the laminated sheet what natural log is? If you pull out your laminated sheet, put in a natural log, I just reinvented the formula. It's centered at 1. You know what? You can't center natural log at 0 because the natural log of 0 right here is undefined. So you have to center it at 1. Kind of makes sense. And so it's a bunch of x minus 1s, but look at that. There's no factorials, but there are 2s, 3s, 4s in the denominator. The signs are still alternating. That's fabulous. So again, if you don't want to do this kind of thing every single time, you could always memorize the laminated sheet. Natural log, you don't have to memorize. Again, sine of x, cosine of x, and e to the x for sure need to be committed to memory. If you can do a few extras, great, good for you. You'll find that you're going to save some time, but it's not an absolute requirement. You can always rebuild them if you have to. And by the way, if you were wondering if our answer was correct, it is. Nice. All right, I typed in natural log of x and graphed it. I know it looks like I typed in log. Well, actually I did, but on a lot of graphers, because natural log dominates the real world so much more than log, a lot of times when you want to type in natural log, you have to type in log. And this is not log base 10 because I am going through the point e, comma, 1. You can see it right here. That's the point 2.71828, comma 1. If that had been an actual log, that would be the point 10, comma 1, and it's not. So that is natural log. So Green Globs does graph natural log. That's good news. All right, now let me go ahead and start putting in my Taylor series that we found together. Keep in mind that natural log is centered at x equals 1. That's where the C is. So right here at the point 1, 0, all the graphs that I make should look very tight-knit, very much perfect. And then they'll start to lose their accuracy as you move away from x equals 1. They'll basically the graphs will start to fray, like rope kind of fraying or hair getting split ends or whatever. So here's the first degree Taylor, y equals x minus 1. Straight line, but man, super accurate just for a short period of time. Right by the black dot, you can't tell how bad that graph approximation really is. As you move away from the black dot, you're exposed. But don't worry, we're gonna tack on some terms. Minus 1/2 quantity x minus 1 squared. Green Globs does not require parentheses around the 1/2. It knows. All right, that's a little more convincing. Let me zoom in a little bit more on that point 1, 0. I think that'll be more impressive. All right, you can kind of see that looks a little easier to see. Everything is perfect right here at the point 1, 0. And the moral of the story, hopefully you've caught on to this by now, is the more terms that you add, the higher the degree, the more and more the graphs are going to look like the red graph of natural log, the way they should. There's third degree. Here comes fourth degree. This will be the last one I have room for. And you can see that's pretty decent. Let me erase some of the other ones. So when you guys type in natural log of something on your calculator, you type in natural log of 567. The graphing calculator doesn't know what natural log is. Instead, the graphing calculator is trained to use a Taylor series expansion. Obviously, it goes past fourth power because this looks very accurate from about here to here. Nobody will be able to tell the difference between the two colors. And then it starts to fray. As you get farther out this way, they start to separate. Same thing as you start to get to 0, -1, you can see some separation. But if you add on some more terms at the end, it'll tighten it up. So that's how calculators are programmed. They're programmed using